So we're going to go ahead and finish the content of Exam 1, and then if you have homework questions, we'll sort of incorporate them into this document. But we did leave off with, there's going to be one question where you're given a rational function, you have to identify the discontinuities, state the vertical, horizontal asymptotes, and the location of the hole using limits. And I don't know that we ever mentioned the terminology, but a hole is, if you think about like when you factor things and then you cross factors out and you say, all right, well, I crossed that factor out, there's a hole there. Holes are referred to as removable discontinuities. Not that I'll test you over that, but you should know that the hole is called a removable discontinuity. They're one and the same. So we have one question for that. There's going to be one question. We have to use the intermediate value theorem to determine if a solution exists. So you'd be given a function on a closed interval from A to B, and we want to use the intermediate value theorem to determine if there is a solution. The intermediate value theorem was in 2.6 when we talked about continuity. So one question over that theorem. There's going to be one question for your one question given a piecewise function. You should be able to determine the intervals of continuity. Intervals of continuity and state if the function is continuous at a point, just say x equals to a. So that'll be given x equals 1 or whatever. Just be sure on a problem such as this that you answer both questions. A lot of times on problems like this on the exam, people will use the limits to justify if there's continuity at the single point, but then they'll forget to list out the intervals of continuity. So we did have a few examples later in 2.6 for something like that. But that's, when you're determining intervals of continuity on these piecewise functions, you want to look at the limit from the left and from the right to determine if it's left continuous or left continuous. Okay, so don't forget the intervals in problems like this. And then one question from 2.7. So you'll be given a function, a limit statement rather. I don't want to write that. I guess generically here. You'll be given this limit statement. Of course, that has the function in it, the graph. And an epsilon. And from that, we want to be able to find delta and be able to identify a f of x and L. So, that's something, for example, you would be given the statement, the limit as x approaches, I don't know, x approaches 1 on 8x plus 5 equals 13. You would be, it's not going to be a linear function, but something like this, you would also be given the graph. And it would ask, what's A, what's f of x, and what's L. So you have to determine those. And then of course, with the epsilon given, then you'll use the graph to find the delta. So that's what that problem from 2.7 entails. All right, and that's the content for our first exam. So are there any homework questions or general questions that y'all have? Yes.
It's not a specific question, but when we do a test and we don't know the answer, can we ask for help after we're done taking it? When we redo it, we have to that answer.
Yeah.
Is that okay?
Yeah. So like after the fact, you mean?
Yeah, after the fact. Yeah, that's fine.
Yeah.
Is that still okay?
Yeah, that's okay. If you have questions after the exam's over, then you can ask me like, hey, how did you do that? How were we supposed to do that particular problem? But during the exam, if you have questions, if you need clarity, you don't understand a question, you just need a reminder, feel free to come ask me. If it's directly related to the question, I might not be able to give you an answer, right? But I can certainly help you try to remember. So yeah, at any point you can ask. After the exam's handed in and your question 7 was really bugging you, then you can ask how that one was done or whatever. Yeah. So make sure you're doing all of your homework and the quiz for Chapter 2. All of it's due at 1 p.m. on Thursday, this Thursday. No one has any homework questions? Hopefully you're not using Help Me Solve This too much. Okay. Well, I'll mention a few things then. In no particular order. So we'll look at the limits at infinity on the sine function. And the cosine function. So what would we say about these limits?
They don't exist, or like they just continue?
So which one? I mean,
Well,
the functions do continue, right? Yeah.
Right. Like that the limit, as x approaches infinity, the limit doesn't exist. It's it's just gonna stay between the interval that it is.
Right, yeah. So these limits for sine and cosine, oops, these four limits, none of those limits exist. Because sine and cosine, you've got to remember what a limit at infinity is meaning in this context. So there's, if you plugged in, with a lot of these, we're able to just kind of plug in infinity and see what the function does. Does it get larger? Does it get smaller? What happens? But sine and cosine are always in between 1 and -1. So like way out at infinity, if you're at 5 trillion, it's between 1 and -1. If you're at 10 trillion, it's between 1 and -1. It never flattens out. So those limits don't exist, and it's important to know because when we compute limits at infinity on some functions, that's kind of where that Squeeze theorem was able to help kind of determine certain limits that involve sine and cosine. If I have an example. So like, for example, what's the limit as x approaches infinity on e to the x times sine x? Well, initially when we look at it, now that we know this, we have e to the x. What's the limit as x goes to infinity on e to the x? Just by itself. It's infinity, right? You think if you can remember the graph of e to the x, looks like this. So we've got infinity times something that doesn't exist. So there's really no other approach we could take at this point to compute this limit other than using a Squeeze theorem. So the idea here would be you're given something to the effect of e to the x is less than or equal to sine. Negative e to the x is less than or equal to sine is less than or equal to e to the x. So something like that. If you were given that, so I mean we start with I guess this statement, which is, and then just multiply through by e to the x to give us a sense of where that's at. Again, if you're required to use the Squeeze theorem on the exam, the inequality will already be provided. You just need to know, hey, based off of this inequality, what does the inequality actually tell me about the function or the limit on the function in the middle? Is everyone clear on that? I wouldn't actually have you come up with an inequality. Okay, so I don't know if I have one like that. Yeah, so I mean that's kind of the idea that we would use to answer that. So as x goes off to infinity, we have e to the x going off to infinity. It's negative infinity. E to the x goes off to infinity. So this doesn't really help us here, right? Because we have the limit on the function in the middle is bound between negative infinity and positive infinity, right? So once we apply that to each piece, we'll just go ahead and write that out. That doesn't help us. But the idea is still here with the Squeeze theorem. If we have this bound between two functions, the limit on the ends, the limit on the middle, it works out when we have the same limits here and here, right? If this number and this number are the same, then we can say something about that limit in the middle. If we sort of take the same approach, so we'll just leave this one. Maybe we'll talk about stuff later on in chapter 4. that will help. But we'll just leave this one. We can't answer this question right now. About the limit as x approaches negative infinity on this one, e to the x sine x. And let's just pretend we were still working with this inequality. So what would we know about the limit at negative infinity? E to the x sine x. Yeah, so I guess you've got to remember the end behavior. Now at negative infinity, and again, just all we're doing is applying the limit as x approaches negative infinity to all of these pieces. So I'm just going to be lazy and write it out like this. But as x approaches negative infinity, what does e to the x approach? It approaches 0, right? Out here at negative infinity, e to the x is smoothing out towards, or flattening out towards 0. So this is approaching 0, negative 0 really, e to the x approaching 0. So what do we know about that limit? It has to be 0, right? If the limit on the function in the middle is larger than or equal to 0, but less than or equal to 0, it has to be 0. So I mean, just because you're given the inequality, I guess it's not, it's not a free question, right? You still need to know how to compute the limits on the two functions on the end. If you end up in a situation where we did in example 1, then you can't determine that limit. So I wouldn't ask you something like that. Situation 2, you've got to remember these two limits on the end to answer the question about the limit in the middle. So, anybody have any questions on it or comments on that? What about the limit at infinity for the sine of 1 over x? Or negative infinity? Does that also not exist? So as x gets larger and larger, what happens to the argument? It's smaller and smaller. It approaches 0, right? So what is this limit? 0, because the sine of 0 is 0. Sine of a number approaching 0 is basically the sine of 0, which is 0. Same thing with negative infinity. You still have 1 over an extremely large negative number, which is an extremely small number. But it's we're approaching 0 through negative numbers, but it's still approaching 0. Same thing for cosine too. If it were cosine 1 over x, so those limits exist. So it's just basically a fundamental idea. Like even if we didn't have sine here, you should know the ideas that we talked about in 2.4 and in 2.5, where it's they're kind of closely related but different. In the sense of a limit, I guess we'll say that in terms of a limit. If we had some number over 0, what would your limit approach if like your work showed this? If I've got a number on top and I'm approaching 0, what would your result be? What would the answer to that limit be? Infinity? Does everybody agree? You got a number over something getting smaller and smaller, your quotient gets larger and larger, right? So these were, I don't know, I guess we can say it like this. Positive or negative infinity. Infinity comes out just because you've got something fixed over something that's getting smaller and smaller. Like that will produce the infinity. The signs on the numerator and the values you're approaching 0 through are the things that affect the sign of the infinity. What about if it's, we kind of answered this already, but in the terms of a limit, if you've got a fixed number over something that's getting larger and larger, your quotient gets smaller and smaller. So nothing ever affects that reasoning. And that's, we saw, I guess, we'll call this 1 and 2. We saw 2 come out with just a sign attached to it, but the same reasoning applied. So those are 2 notions of limits that you should definitely know. A lot of times if you get into these situations, people are inclined to say that the limit doesn't exist. It's true in this case, this limit doesn't exist. But when we write infinity or negative infinity, it's more descriptive, because if a limit ever evaluates to infinity or negative infinity, what does that tell us about the function? What kind? A vertical asymptote, right? If you just say, hey, this limit on this function doesn't exist, and you just stop there without going a bit further, you don't have any information about that function. But if we know that the limit doesn't exist because it's positive or negative infinity, then whatever we're approaching, whatever x is approaching, you know that's a vertical asymptote on whatever function you're dealing with. So it's a little bit more descriptive when we write out stuff like this, even though the limit doesn't exist. So you really want to think about if you're just going to say the limit doesn't exist, like why it doesn't exist. Does the limit from the left and right not equal? Is there a vertical asymptote? Like what's happening, right? Okay. Does that make sense? Does anyone have any questions on what I just said or need clarity? So in the instructions I'll have evaluate the limit or state that the limit does not exist, and state that it's positive or negative infinity when it's appropriate. Okay. All right, did anybody think of other questions you had? Okay, see y'all Thursday. I'm just kidding. I don't know that I have other things to look at. I guess there's a couple.
Roughly how many questions is there? Roughly how many questions is there?
Like 5, 6, 7, 21.
Roughly like what we have for your student else was multiple choice, true, false.
Yeah. Yeah, so I don't remember how many. I think there were like 3 or 4 of those. So there's like 25-ish questions. Yeah. You do have the whole class period to do it. So. All right, let's, so with the multiple choice true, false, short answer stuff in mind, types of questions that could appear. So let's just say if the limit as x approaches a infinity, or the limit as x approaches a on f of x is negative infinity, then the limit as x approaches a on f of x does not exist. So I guess true or false? True? What do y'all think? Yeah, we just talked about that. Not necessarily. It really depends on what f of x is. So like these true, false, short answer questions usually are very generic like that. So you don't, it's hard to answer these sometimes because oftentimes the first thing that pops into your head isn't the only outcome. So the first thing that pops into your head, maybe not with this one, but with questions similar to this, the first thing that pops in your head, like the scenario seems to work out. But if you think about it a little bit differently or come up with a different type of function, then it doesn't work out. So, I think that's why some of these are I don't know, people usually hate these questions, but they're a lot more conceptual to see if you can kind of grasp the bigger picture is really what it is. All right, sorry I didn't write these questions down. I'm pulling them from your textbook. So how about, we'll call that 1. 2. If the limit as x approaches a on f of x does not exist, then either the limit as x approaches a on f of x is infinity, or negative infinity.
False.
So I guess that one's true or false?
That's false.
False? False? Anybody have something different? So if it's false, why is it false?
There's other scenarios.
So that
There's like other options. It doesn't just have to be those two. Like it could be a whole, for example, at A.
okay,
It could be something like that. Different scenario.
okay, different scenario. Yeah. So we've seen different scenarios that particularly fall in line with this. What about, a function like this?
Well, the limit isn't equal to the function.
Right. So there's a limit. There's an example of a limit that doesn't exist, but neither of those limits are infinite, right? So it is false. Here's a counterexample. You can think of other counterexamples too, I'm sure. Let me go back up there. Does anyone have any questions on that one? Okay, we'll look at one more. So let's say if the limit as x approaches a on f can be calculated by direct substitution. By direct substitution, then the function is continuous at x equals to a. What do y'all think? I'm not gonna let the same three people answer. Somebody else has to be vulnerable.
True.
True? Okay, what are you thinking is true for? Anything?
Can't directly substitute a function that is, or something that's being divided by 0 or something that equals infinity.
Okay, so you're thinking about division by 0, like in the sense of me asking you to compute a limit like this, for instance. So we know that 1 over x isn't continuous at 0, so we can't just plug that in, right? I guess we can come back to this here. So you really got to think of scenarios that we've encountered through your homework or in class. But yeah, we also said that the why behind direct substitution was based on continuity. So we wrote that down in 2.6's notes somewhere. Anytime you're able to directly substitute, it's because the function is continuous at a. So yeah, it's true. You know, and again, us saying that 1 over x isn't continuous at x equals to 0, it doesn't keep us from determining the limit per se, right? We can't plug that value in to determine the limit. So what we did with these, like we did above in the last page, was we said, all right, well, the numerator still is approaching 1, the denominator is approaching 0 through, positive or negative values, depending on what direction we're approaching 0 through. So 0 from the right or from the left gives us something like that, which would give us 1 over 0, fixed number over 0 in the sense of a limit that automatically gives you infinity, and then the sign over the sign gives you the sign on the infinity. So we still can analyze those limits. It's not that, I guess these two concepts are related, but don't let it confuse you as to say, oh, this function's not continuous at 0, therefore I can't evaluate the limit, because you can. All right, so those are the types of questions. When I say conceptual questions, that's what I mean. They're very broad and generic questions. Is everyone okay with these? Any questions so far? Okay, we'll do one more. So the value of the limit as x approaches a on f of x, if it exists, is found by evaluating f of a. Okay, anyone on this side of the room want to Be brave. False? Okay, so false. What do y'all think? So this is kind of another way to answer the question above, right? So there's multiple ways to answer this. When is the value of this limit equal to f of a? So I guess we could say when does the limit as x approach a on a function equal to f of a? When does that happen?
When it's continuous.
Good, when it's continuous at a, right? When the function is continuous at a. When f of x is continuous at a. But right, the answer is false. Or the question is false, or statement rather is false. Yeah.
I have a question. It's on the homework.
Okay.
I wanted to see if you can work it out.
Sure. Is it like one of these, or is it like a
No,
just
it's
a
the
regular
one.
example?
Yeah, it's the 2.5 on the online.
Okay, cool. All right. Does anyone have any questions about that?
I was going to say, can you also just say it's found by computing limitation as you're coming from both directions, positive and negative? Can you
So-
put it that way?
It's found. By computing the limit from the left and the right,
Yeah.
and so our question's still the same. What about this statement here? No, we would find it by computing the limit from the left and from the right. What do y'all think about that? So really the whole thing hinges on if we're going to compute the limit as x approaches a, if it exists, and we're going to say that it's equal to f of a, really that whole thing is based upon the continuity at a, right? So if this function is continuous at a, there's really two things we need to address. If the function's continuous at a, do we need the limit from the left and from the right? No, because limits from the left and from the right are when you have possible discontinuities, right? Asymptotes, breaks or gaps in a piecewise function, that kind of thing. So if the function's continuous, then, I mean, I guess that statement is correct, but it's incomplete. Because if we compute both of these, they're the same. So these two things are equal if the function's continuous at a. If the function's not continuous at a, yeah, so I don't know. I maybe give partial credit for that because it's kind of not addressing the question. I guess, something to the effect of, that might be relevant. Let's just say here, if x is continuous at a, sorry, if x is continuous at a, sorry, f of x rather, if f of x is continuous at a, then those two limits are the same. But it doesn't really tell us how to evaluate them, right? Like the limit from the left and from the right, it could be like a jump in a piecewise function. We could have like a vertical asymptote situation happening when we compute these limits. It's not really addressing the question like how you would evaluate it, right? You're just saying that, I don't know how to put it, but you're not addressing the question or how to evaluate it. If x isn't continuous at A, then these things might not be equal. They could be equal too, right? We saw one piecewise function where it was connected, but we've seen other piecewise functions where the pieces are separate. So those limits might not be the same. Here it's continuous, but here it's not. So yeah, I don't know if that was helpful, but okay. Any other questions on this kind of stuff? All right, so
That was section 2.5, question 13.
okay. As you have it, I can pull it up too if you don't.
Yeah.
So we have to find the limit at infinity and at negative infinity of f of x for the following function. I'm going to highlight this here, evaluate the limit at infinity and negative infinity for the function. What's another way to ask that question? Right, and behavior. So instead of saying evaluate this limit and that limit, it could just say state or determine the end behavior of the function. There was one particular type of function that we looked at where the limit at infinity and the limit at negative infinity would be the same. Does anybody remember what kind of function that was? Okay, if you don't, then if it asks for end behavior, you have to compute both of these limits. But there is a function where both of those limits are the same, assuming that we do have a horizontal asymptote. Okay. So end behavior, limits at infinity, these things are the same idea, and both of these things are telling us where the function has a horizontal asymptote or asymptotes. Okay. This one seems familiar. Yeah.
Data, you could describe the leading terms.
Yeah. Do what?
I said data, you could describe all the leading terms.
The leading terms, yeah. So that's kind of how we're going to look at it. I'm just going to start with this function and then look at the limits in a minute. I'm just going to rewrite it because we're going to simplify it. All right, and also we've got to remember that when we say look at the leading term divided by the leading term or the dominant terms, that's only applicable when we're computing a limit at infinity or when we're determining end behavior. Any other limit, these other terms that would get ignored at infinity, any other value, they are important. They do affect the overall outcome. So it's only at infinity or negative infinity. So we'll say that at infinity or negative infinity, this function we could view as leading term on the top, leading term on the bottom. But you got to be careful here. There's actually two leading terms on the bottom, right? We've got the 4x cubed and the 64x to the 6th. The plus 8 on top and the plus 3 under the radical definitely don't affect at infinity or negative infinity. Because again, loosely, hopefully, you're thinking about this, the square root of 64x to the 6th. You're kind of thinking of that as 8x cubed, right? So I can't ignore that term because it still plays a part with this other leading term right here. And then how does 64x to the 6th, how should that be simplified? Okay. Okay. This or this?
That way.
That way?
Yeah.
Remember when you take a root of something that has the even root of something, I don't know, whatever's here, and you get that thing to an even power, that's fine. You don't need absolute values in that situation because whatever's in here to an even power is going to be positive. But when you do this of something and you get that quantity to an odd power, then you need absolute value there. Because sometimes the thing inside raised to an odd power is positive, but sometimes raising something to an odd power is a negative. So yeah, we took an even root, we got an odd power as a result, we need the absolute value there. So there's a few ways that we computed these. This isn't the only way to think about it. But really with this term right here that we've simplified, there is only one way to think about it. At infinity, you've got to make sure you're using the positive version, and at negative infinity, you have to use the negative version. Okay. So we'll simplify this just a bit more. We don't need the absolute value around the 8, just the x cubed, because 8's always positive. So we have 8 times the absolute value of x cubed. And so now this is how we simplify the absolute value of x cubed really depends on where we're at. But is everybody okay with that? Are there any questions? So if now we compute the limit at infinity, this thing that we've simplified we're out at positive numbers, right? If I square or cube any positive number, it's always positive, right? So the absolute value in this instance for large positive numbers is not needed. Limit at infinity on this function is the same thing as the limit at infinity on this function. Is that okay? Makes sense? Okay. So then we're going to look at, like we did with any of these, now we've got this polynomial over this polynomial. Leading term up top is 1x cubed. Leading term on the bottom now is 12x cubed. So I'll just write this out in one more step. X cubed over 12x cubed. And what would that limit be? Yeah, 1 over 12, right? So what changes when we compute the limit at negative infinity?
A to the cube, that would be negative, right?
Right. So at negative infinity, now we're approaching, now we're going through negative numbers. And so the absolute value of x cubed I'm just going to write this out so we can see that. A negative number is the absolute value of x cubed, so it's crooked, is negative x cubed. Because all those negative numbers out towards infinity are square, we're cubing them, so they're all negative. But in order to make these things that are negative positive, we just gotta multiply them by -1. That's what we did. Okay. So then this limit, we write it here. We've got 1x cubed on top. -4x cubed on bottom. So that limit will be what? Yeah, -1/4. You got to think of them this way, especially when, I guess, just think of them this way, because a lot of times, you know, the one we did in class, it was like the at positive infinity was 2, and at negative infinity was -2. There was another one that's +1/2 and then -1/2. They're not always opposite of each other, just because towards positive infinity you've got the positive function, and towards negative infinity you have the negative of that function. They're not always opposite. It really just depends on what function you're dealing with. So it's better to know these methods than to try to look for a shortcut. Does anyone have questions on that? Okay. Yeah.
Can we do number 8 on 2.5 as well?
Yeah, sure. I think we'll start a new page. So the limit at infinity for this one. So the leading term up top. Sorry, just habitually. Leading term on the top. And again, we're doing this because we're approaching infinity. Divided by the leading term on the bottom. Well, what's the leading term on the bottom? Yeah, the square root of 49w to the 4th. Right? In this sense, even though these powers are like super close out towards infinity, this thing right here, it's a lesser term than the w to the 4th. So we have technically on the bottom the square root of 49w to the 4th. Okay. What's the square root of 49w to the 4th? Right. It's 7w squared. Do we need absolute value there? No, because w squared is always positive. So what does that simplify to? So this first situation that we have here on the whiteboard is the most straightforward. You really don't have to think about it. If you're approaching positive or negative infinity, you simplify an even root as an even power. Both of those limits are going to be the same. Questions on that? So again, whether we approach positive infinity or negative infinity here, the limit's still going to be 8. Okay. Any other questions about these or different questions?
On 2.6, can we go over question 11?
5.
2.6.
2.6 question 5?
No, 2.6, question 11.
11, okay. I don't know who else copying this down, but we've got a piecewise function, and we want to use the continuity checklist to show that the function is not continuous at 1, and then answer the question, is f continuous from the left or right at 1, and then state the intervals of continuity. So this was what I was referring to. One of those, I think it was that next to last piece that we wrote down for the content of the exam, where it says you're given a piecewise function, you want to state the intervals of continuity and determine whether it's continuous at a point. So this is like a perfect example for that question. Okay, so the function, we're going to show that the function is not continuous at 1, but in order for this function to be continuous at 1, what has to happen? Do what?
The function has to equal 1.
The function has to equal,
The limit.
right, so that's like an algebraic way to look at it. Like these two pieces have to coincide on the same y value. From our calculus perspective, what do we have to do?
Yeah, so equal the limit.
We have to involve the limit, right? So what has to be true about the limit?
Well, the limit has to be equal to the function value. And
Yeah.
of course, both of those things have to exist for that.
Right. So let's just write here, before we do part A, 'cause it's a weird way to ask that question, we're going to say if f of x is continuous, at x equal to 1, then what has to happen is f of 1 has to equal the limit as x approaches 1. Right? The function value has to equal the limit. So granted, looking at this from an algebraic perspective, if I plug 1 into this function, where's the y value? If I plug 1 into the bottom function, where's the y value? If the y values are the same, then the pieces meet, it's continuous, right? Don't do that. That's an algebraic way. Whenever you're asked anything about continuity, you gotta think in terms of limits. There's gotta be a limit involved, some way, somehow, for you to justify continuity fully. So this is kind of what we're gonna address. Show that the function's not continuous. Either, remember the checklist, either the function at 1 doesn't exist, or the limit doesn't exist. Either way, they're not the same thing. In order for the function in order to show the function is not continuous, we have to have something like this, thought B is violated. So part A, we're going to compute, and I'll just write number 1 from the continuity checklist. Item number 1 on that checklist, what is f of 1? That's the value that we're trying to determine continuity at. F of 1 is equal to 4. Does everybody agree? F of 1 is equal to 4. Okay, continuity checklist item number 2 says we've got to compute the limit as x approaches 1 on f of x. Maybe I'll write this below. How do we do this? How are we computing this limit? From the left and from the right, does everybody agree that we have a one-sided limit here? We can't answer the two-sided limit question immediately, so we have to do the one-sided limits. So this is like number 2, part 1. What's the limit as x approaches 1 from the right on f of x? And from the left. So now that we've broken this down in this sense, we need to just keep track of what we're doing, because now we're looking at the limit as x approaches 1 from the right. We're going to be able to say something about continuity from the right once we've computed this limit and compare it to the function value. Same thing over here. For the second part, we're going to be able to say something about left continuity once we compute that limit and compare it to the function value in number 1. Okay. So if we're approaching 1 from the right, on the function we're using which piece?
First one.
Yeah, x squared plus 4x. So this is the limit as x approaches 1 from the right on x squared plus 4x. So 1 from the right, x squared plus 4x, that limit is what? 5. Yeah, we just kind of, now that we know the function, we just ignore from the right. We're just plugging 1 in, 1 plus 4 is 5. So stop right there and then determine what your work shows you. Okay, I've computed the limit from the right at 1. I'm comparing this to the function value. This isn't the same thing as my function value at 4, which was 4. So what do we know? So like this, but this doesn't tell us, just because this isn't the function value, I guess we could say that, we could infer that the limit doesn't equal the function value, therefore it's not continuous at 1. But so like what we're gonna see is you know, just going through this process, it's gonna tell us all of the pieces. It's gonna tell us, I believe, just going through what we're going through, it's gonna tell us it's going to tell us all 3 of these pieces just going through this procedure. So this is the procedure I would go through on any question like this on the exam. And all we're doing is using the continuity checklist, realizing we've got to use two-sided limits. And from the two-sided limits, now we can state what's true about continuity from the right. Is this function right continuous? No, because we don't have it equal to the function value. F of x is not right continuous. At x equals 1. And again, don't just stop there. This is kind of like, you can write that out if you want, or you can just keep that in your head. When we say that the function is not right continuous at x equals to 1, by saying where it's not continuous, we're implying where it is continuous. So this means the function is continuous on what interval? Like I'm approaching 1 from the right. Bill's right. I'm approaching 1 from the right, but the limit isn't the function value. So what happens at that endpoint? Is it included or excluded? It's excluded. So I'm approaching 1 from the right. The function, or the endpoint here is not included because that limit from the right isn't the function value. So we're continuous on this interval. everybody okay with that? Is it also true at this point we can say the function isn't continuous at 1? So we can answer part A, right? Because if the limit from the right doesn't equal the function value, doesn't matter what if the limit from the left did. Let's say the limit from the left did equal 4. The left and the right limits aren't the same, therefore the two-sided limit doesn't exist, right? So let's remember this, because we were asked for intervals of continuity. We already have half of the whatever, part B or part C, I don't remember. And then we'll do the same exact thing for the limit at the from 1 from the left. So we're going to use the function 4x to compute this limit. We're going to get 4 there, and again, we're noting that this is the function. Sorry, I'll do this in a different color. We're noting that this is the same as f of 1. So what do we know about continuity here from this piece? It is left continuous at 1. So again, maybe you don't have to write that particular statement down. Your limit equaling or not equaling the function value is showing that. We're just writing that out because that's what you should think about when you see this type of situation. So it is left continuous at 1, so we know what interval this is continuous on. So we're going to say that is f of x is continuous on what interval? Good. Negative infinity to 1 included?
Yes.
Because we have left continuity there. So there we go. You have the intervals of continuity clearly stated. The limits aren't the same. Our limit from the right was 5. The limit from the left was 4. So then, kind of from this point, we've got all of this information. We can go back up and ask what's the limit as x approaches 1 on f of x. The right limit and the left limit are different. This limit does not exist. So we'll just say, I don't know, I'm just going to say part 1 doesn't equal to part 2. And, oh, that's pretty implicit. So if you want to address these things as like a one-off, just so you're keeping track of what you're addressing, then feel free to do that. But we do sort of get all of it with one shot and using the checklist. Okay. So the limit doesn't exist. Come back here and say item 3. F of 1 does not equal to this limit. Thus, f of x is not continuous. At x equal to a. So that's really part 1. We've shown that the function is not continuous at x equals to a. If that's all we had to show, then you don't have to show all of this work, right? But we also wanted to show the intervals of continuity, which involved showing, the red and green up above. So I guess that's part A. Just to kind of condense all of this. Is the function continuous from the right, from the left or the right at 1? We said that it was continuous from the left at 1. So from our interval here, f of x is left continuous at x equal to 1. And in part C, we have our intervals continuity here from, was that 1 to infinity, and this one here. I guess that's it. Okay, does anyone have any questions on that? Okay, so we'll take a break and then, if y'all have more questions from the homework or the review, we can go over those. I do have other things that we could look at if you want, if you don't have questions, so. We'll take a break. All right, does anyone have any other homework questions? All right, let's look at this example. So you're given f of x is x minus 6 over x squared minus 36. You want to identify any discontinuity. Any of the discontinuities, which again are holes, removable, and vertical asymptotes. And I guess if there are any holes, list the ordered pair. And determine the behavior. Near any vertical asymptotes. Using limits. So for both, use limits, not algebra, to determine this stuff. And we'll also state if f of x has a horizontal asymptote. Also here, use limits. So, I mean, you can use algebra to determine information, but as far as like showing the work to justify it, you need to use limits, okay? So when we look at this function f of x, we can start off through an algebraic perspective and say, all right, well, that's just x minus 6 over x plus 6 times x minus 6. And simplify or reduce this function to 1 over x plus 6. So I mean, that helps us get our bearings. What do we know from our work now? There's a hole where at?
6, 1,
Or removable discontinuity when x is equal to 6. And what else? Say that again?
The ordered pair would be 6, 1/12.
Yeah, so we're gonna show the ordered pair using limits.
Oh, yeah, because the limit as x approaches 6.
Yeah, exactly. Right. But what else do we know? Right. Yep. So the factor left over x plus 6 on the bottom, we know that corresponds to a vertical asymptote. Okay. So, I mean, that's the extent of the algebra we want to use. It says determine the ordered pair for the whole using limits and the behavior near the asymptote, vertical asymptote using limits. So I guess there's a few things to compute. We're going to compute the limit as x approaches our removable discontinuity, the limit as x approaches 6. And it's, you know, it's your choice whether you want to write out the original function or just write out the simplified version. So I don't know that this first step that I've written down is absolutely necessary because you've already factored and simplified. I don't know why I switched colors, but. So this is for our whole because we identified it at 6. X approaches 6. The function approaches 1 over 6 plus 6, which is 1 over 12. So that tells us that we have a whole or removable discontinuity at 6, 112. Remember the algebra approach when we cross this factor out, we're only able to do that when x is not 6. And that's what's happening here as we approach 6. X is not 6. So this is technically why that factor crosses out. X minus 6 over x minus 6 is not always 1. Like we said, it's not 1 whenever x is equal to 6. So just from like an algebraic standpoint, there's some gaps missing when you just factor and cross out stuff like that. It's made more technical by the limit and the fact that x isn't 6. Okay, so there's the whole. The vertical asymptote, you need a limit from the left and from the right. So when we approach -6, we have to approach from both directions. So we're going to do part 1, the limit as x approaches -6 from the right and from the left. So, well, you know, again, we've already simplified that function, so we're just going to write it out like this. Now you can check your work to see if you're analyzing the limits correctly by your algebra approach. Or you just plug points in to see if that's a really large positive number or a really large negative number. But somehow you need to be able to determine that from the limit. As x approaches -6, the numerator is fixed at 1. It's super clear that the denominator is approaching 0. So we know that we're going to get an infinity or negative infinity out of both of these. So we just need to look at the sign. As we approach -6 from the right, we approach, or x plus 6 approaches 0 through what values? Positive or negative values? Positive values, right? You have numbers that are slightly smaller than -6, and those numbers added to 6 are small positive numbers, right? So if you want to write just I'm approaching 0 through positive numbers, if you want to indicate that the denominator is small and positive, however you want to denote that, please do something to that effect. So 1 over 0 as a limit gives us infinity. We've got a positive over a positive gives us a positive infinity. Similar thing here. We're approaching -6 from the left. The number is slightly larger than. Okay, this is how we going to say that. So this, so the denominator approaches 0 through what kind of values? Negative. Does everybody agree? Negative values there. So this is negative infinity. So that's really what we mean by show the behavior near the asymptote by using limits. We're computing those infinite limits. And again, like if we're visualizing what's happening, now we have a clear picture here at -6. Here's our vertical asymptote. It's terrible. And so we know the function from the right of -6 is approaching positive infinity. So, you know, the function's over here doing something, but as we get closer and closer to our asymptote, the function's up here. From the left of -6, as we get closer, the function's way down here. Questions on any of that? So those are the discontinuities. Used limits to show, you know, what's happening at the discontinuities. And then I guess part 3 we would compute or try to find the horizontal asymptote. So how do we find the horizontal asymptote? Using limits. What do we have to compute? Leading terms, right, because that's only because to find a horizontal asymptote we have to compute
The limits at
at infinity, right? So finding a horizontal asymptote is finding the end behavior, which is computing a limit at infinity and negative infinity. Those are all 3 the same thing. So we're going to take our function, compute the limit at infinity. I mean, you can use the simplified version or the original version. I would stick with the simplified version just because it's simpler and that's what your limits above simplified to. But if for this, it doesn't matter. For consistency, I would just, if it simplifies, use the simplified version if you're confused. So what's the limit here? As x approaches infinity, 1 over x plus 6 approaches what? 0? What do y'all think? Numerator's 1, denominator's getting larger and larger, quotient gets smaller and smaller. What about at negative infinity? Still 0, right? Still 0. So what do we know? Horizontal asymptote at
0.
y equals to 0. So this was what we sort of alluded to earlier. When you compute limits at infinity on rational functions, if it has a limit, they're going to be the same at positive and negative infinity on rational functions. We saw that wasn't the case with the, you know, the x cubed over the square root of whatever. We didn't see that actually happening. With rational functions, it does happen. Rational functions do have at most 1 horizontal asymptote. So whether you're out here or out here, if it has 1 horizontal asymptote, it doesn't matter where you're at. It's still the same. So on rational functions, if you recognize or realize that, I'm okay with you just computing 1 limit at infinity, not both. All right, and then so we can go back up to our graph and say, where was our hole at 6, 1/12? So over here at 6, over here at 6th, 1/12, you know, somewhere around here we have a hole. We have this line being now our horizontal asymptote. And so we can sort of fill in the, we can fill in the gaps here. It's supposed to be flat. Let me try that again. That's great. That's a little better. That piece is here. Horizontal asymptote is here, so we know the function is hugging it in this direction because of our prior work that says it's down here, right? So we can get a pretty decent graph from just that information. I guess decent is relative, but any questions on that? Is there any other types of problems y'all want to look at?
Can we do something like from 2.7?
Yeah, it's from 2.7. And we can look at some more limits too, because there are like 14 questions on the exam about limits. Also, if you have time or want extra practice, you can do this exam review that's not graded. So those are just additional practice problems, more or less. Let's go with this one. I guess that'll be okay. So it's similar, like an exam question would be, you're given this thing right here. You would actually have the function in here though. So like the function would be specific, it wouldn't be f of x. And then you would have this graph and it would say perhaps, you know, find delta when epsilon is 1. Something like that. So this is the limit as x approaches 2. I just want to go on down to here, the x-axis, and mark 2 because that's, I'm going to count from the left and from the right of that value that x is approaching, and the limit is 3. So I want to mark that on the y-axis. Here at 3. And then what it says is we're going to let, in part A, let epsilon equal 1. So remember, epsilon was associated with the y values. Epsilon is the distance you are from the limit on the y-axis. So all we're going to do is go up 1 unit from our limit and down 1 unit. And And then we're going to use the function to give us a window around 2 on the x-axis. So lower bound, epsilon is 1, gives us 2. We're going to go down to the x value, which is at 1. Epsilon is 1, puts us as an upper limit of 4. So we're going to go over to the function here, down to the x-axis at 6. Is everybody okay with that? Just make sure when you have to report what delta is, that you're starting at the a value. Whatever x was approaching, we've got to count from the left and from the right of that.
So like for this one example, since delta will end up having to be the lesser of these two distances,
Yeah.
would it be all right if we can say, well, visually I can see that one of them is going to end up being shorter than the other, and then just
Sure.
do that one instead of
Yeah.
the other?
Yeah, I think that's fine. We're just looking at this from a very limited perspective. So if, once you draw this line here, you can say, oh, visually, that's going to be the shorter distance than this one over here. It's not necessary to draw this other one, if you can see that. If you can't, then fine, just draw it out just to make sure. I'm counting from 2 to 6, gives me 4, and from 2 to 1 gives me 1. So you take the smallest of the two for delta. So that's a delta of 1 when epsilon is 1. 1/2 will do the same thing. I'm only going to give you 1 on the exam, so you're not marking stuff and then having to erase it. So
Okay, with different colors.
yeah, I'm fine with that. Any other questions about that? All right, any other homework questions I want to look at? Yeah,
On section 2.7,
number
number 1.
1. Yeah, let me label this as number 6. It's really large. So we're given that y lies in the interval 4, 18, and we want to know what's the smallest value of epsilon so that the inequality is satisfied. So the restriction here is this interval, right? On the y-axis, we have to be from 4 to 18. The inequality here is telling us what? Right, so we want to be within a certain distance, epsilon of 11. So wherever that's at, 11's here. What epsilon gives us keeps us within that boundary? 7 from both directions. 7 here and 7 here. So that's what epsilon would have to be. To keep us within that window. Yeah, it's sort of like the first couple of questions I think are like in pieces, and then it's like when you look at the graph, you kind of put those concepts together. Yeah, so it's kind of weird, but. Okay. Everybody cool with that? Okay, we're gonna, I guess, look at some limits. the limit as x approaches 10 on 18 pi cubed? $18 pi cubed, what do y'all think? 18 pi cubed. There is no x in there, right? So this 18 pi cubed is just a constant with respect to x. Same thing if I ask you, what's the limit as x approaches 10 on, I don't know, 12, right? Answer is 12. Y value is always 12. What was I gonna say? Oh yeah, you should have a calculator for this exam. Maybe not necessarily to answer the limits and all of that, but the question from 2.1, it's gonna involve you plugging, funky decimals into a certain function. So a calculator would be super beneficial.
You have set decimal places you want to throw out too?
I think I said 3. Yeah. So since we're talking about that, if you need to round your overall final answer to 3 decimal places, you should definitely have more than 3 decimal places in your intermediate calculations, right? So like if it's 2.37 is what you get for the position at some value, and then the position at another value over whatever this difference is. I don't know. If this is your calculation, then you're going to be off. The final answer is not going to be correct to 3 decimal places. So this intermediate calculation, you need a couple more decimal places. Whatever that is, I don't know. Just making stuff up. So keep that in mind. I do see that it's not a huge mistake, but you got to be technical with it. If you've got around to 5 decimal places, you want 5 or 6 or 6 or 7 decimal places in your intermediate computations. So keep that in mind. All right. So a couple more limits here. So do the limit as x approaches 1 from the right, and our function is the square root of the quantity x minus 1 over x minus 3. Yeah. So what's that limit?
0.
Would it be 0? As x approaches 1? The limit's 0? What do y'all think? Seems like maybe it's a possibility, right? Definitely the numerator's approaching 1. Or 0, rather. If I approach 1 from the right, what's the denominator approaching? A negative number, right? So what does that mean? Yeah, it's an imaginary number, so it doesn't exist as a real number. It doesn't exist. So it's not because we get 0 up here that it's, we need to stop, but this is a negative number. the radical. What about the limit as x approaches 1 from the left on the same function? So top still 0.
Would it be fair to say that it's 0 but through negative values? So like when you get, like it will end up being a negative over a negative.
Yeah, right. So this is kind of like when we're thinking of it like this, it's kind of limiting. So if we're approaching 1 from the left, if I subtract smaller numbers than 1 from 1, I get a negative number, right? If I subtract smaller numbers than 1 from 3, then I also get a negative number, right? So even though I have a negative on top and bottom, when I divide it, I'm still taking the square root of a positive number that's getting smaller and smaller. So it's like, you know, if we just plug 1 in, we're going to say, well, the top's approaching 0 again, and the bottom's approaching a negative number. So then we see like why this is sort of limiting in this case. So it's not that like this is a trick question or anything. It's just that, you know, sometimes with funky things, when funky things have a tendency to happen, you know, you should stop and think about it a little bit more. You know, what we've seen in class, like asymptotes, things approaching 0 or infinity, like those things don't change. So like, I don't know, maybe a better way to think about these things, if there's any question, like this function approaching 1 from the left or the right, there's some weird things going on. So maybe a better way to look at it is to say, what's the domain, to think about what's the domain of this function. And if you don't remember, then maybe we'll talk about it. I think it's a good exercise for us to remember a couple of things. So the thing that we take the square root of has to be positive or 0. So we can say, all right, well, when is that positive or 0? So basically we now have this rational inequality to solve. And really, we answer that question not by like, I mean, you could graph this and see where is the function above the x-axis, or is it below, right? But that's kind of tedious. What we do say is, when does this function equal 0? And undefined. So when's the function undefined? At x equals to 3. When's the function 0? At x equals to 1. So what that does is now give us, right, we're trying to determine where it's positive. We first figure out where it's 0, because outside of where it's 0, it's either positive or negative. Okay, so we now have where it's neutral. At x equals to 1, it's 0. At x equals to 3, the function's undefined. So I'm just gonna do this because the function's undefined. And then we can just pick test values. You can say, all right, well, I'm going to pick something out here, like 0, something in between 1 and 3, like 2, and something outside of 3, like 4. And then those test values go into the x minus 1 over the x minus 3. So when I put 0 into this, I get negative 1 over negative 3. That's positive. When I put 2 into that, I get 1 over negative 1, so that's negative. And then I put 4 into that, I get positives. So now I know exactly, with this chart, I know exactly how to answer this question. when is that function larger than or equal to 0? Well, we go from negative infinity to positive 1. We're including that, right, because that's where the function was 0. Negative infinity to 1. And then from also positive from 3 to infinity. We're not going to include the 3 because it's an asymptote. So that square root of all of that function's domain is right here. And so now when we see, hey, approach 1 from the right, you can clearly see that we cannot do that, right? Because if we're approaching 1 from the right, we're approaching it through this space right here in our union, right? So 1 from the right, like we said, that limit does not exist. It doesn't exist because values from the right of 1 aren't even in the function's domain, so there's nothing to approach through. But as we approach 1 from the left, we can totally do that, right? We're approaching from this direction. The function is left continuous at 1, so we can approach that value from the left. Right? So as we approach values from the left, you know, like a way to think about it is well, I know from these values as I approach 1 from the left, my function's always positive, right? But that's telling us that this function with the radical x minus 1 over x minus 3 is positive. Sorry, without the radical, x minus 1 over x minus 3 is positive. Therefore, I can take the square root of any of these values as I approach 1 from the left. Does that make sense? Okay. So as I approach 1 from the left, like we said, what happens here is the numerator gets closer to 0. But it's getting closer to 0 through negative numbers, right? Or through negative values. 0.99, 0.999. So I have to think of it that way. I'm getting closer to 0 through negative numbers. I mean, maybe not, I don't know, but we're going to think of it that way. And then as I approach 1 from the left, what does my denominator approach? Negative 2. So I have a negative 0 over a 2, right? It's still 0. So I can do that. That limit is 0. This limit doesn't exist. So I know that was sort of a long-winded way to look at that, but I'm not saying there are any on the test that you have to look at like that. But, you know, still having some of these skills can help you out a lot sometimes. Okay. Are there any questions on that? Compute the limit as h approaches 0. Our function is the square root 5x plus 5h. All of that minus the square root of 5x, and then all of that is over h. And it also says where x is larger than 0 is a constant. I think that's a weird way to say that. So basically, x is a positive constant, is what it's saying. That's just how they wrote it. It's kind of weird. Okay, so with limits like this, you know, when we evaluate them directly, and you get like something goofy, doesn't necessarily mean that it doesn't exist or whatever. You wanna think about it a little bit more in depth. As h approaches 0, what happens to our limit, or what is the limit of this function? So we'll just say, like, directly substituting this in, we get what? Something that does not exist is technically not correct, is not a correct way to describe that.
Maybe something that's just approaching infinity.
So why do you think it's approaching infinity?
Well, because if h is approaching 0, then it's just constantly getting smaller. So whatever the numerator is, it's just going to be getting bigger and bigger.
Right, so we said that this thing approaches 0, or sorry, infinity when the denominator is getting smaller and smaller, but what has to be true about the numerator?
It has to be a constant.
It has to be some fixed number, right? I don't know that we ever stated, but the thing is it can't be 0. So if you have something like this that does approach infinity, but it's not what we have, because what we have is really 0 over 0. So that's kind of the problem with this one. If the numerator was like anything else but 0, like whatever number but 0, then we could say that it approaches infinity. But 0 over 0 is not something that we can determine. Remember this, 0 over 0 or any infinity over any infinity. Those things can have any value. They might not exist, they might equal 5, they might equal to negative 20, but these two things can have any value. Now, in the sense of a limit, you've got a particular function, so they will have a particular value. But just as general statement involving limits, 0 over 0 or infinity over infinity can have any value. So we call those, the technical name for that is indeterminate, because you can't determine the value. It's not 1, it's not 0, it's not infinity. Indeterminate, and that's really all you need to know. We see these things in 4.7 again. But if you end up with 0 over 0 or infinity over infinity, you know that there's going to be some, at this point, there's going to be some simplifying that needs to be done. Is everyone clear on that, between the differences that we talked about earlier versus what we're doing now? Like super, super crucial. So if you get a limit that's infinity over infinity or 0 over 0, you probably need to factor it, find the lowest common denominator, involve a conjugate, something to that effect. And so what would we try here then? Do what? So we couldn't square the entire thing, because what we're asked is compute the limit as h approaches 0, and we're given that whole thing as a function of h. If we're going to square this whole thing, then we're not working with the function anymore, right? You're working with the function squared. So I mean, if we were to do this, then we would have to apply the inverse to the result. Sometimes that works, sometimes it doesn't. So what was the deal with when we had radicals involved? Yeah, you want to use the conjugate. So we're going to conjugate the numerator, multiply that result on top and bottom. So we're going to look at this as the limit. What's the conjugate of the numerator?
Multiplying it by positive sign.
Yeah, the positive sign changes. So let me do this. Multiply by square root of 5x plus 5h plus the square root of 5x on top and bottom. If you don't want to keep writing limit as h approaches 0, then just just work this algebraically like that, simplify it as far as you can, and then compute the limit as h goes to 0. But at some point, you need this limit here. Okay, so when we multiply the numerator out, what do we get?
Five x plus 5h minus 5x.
Yeah?
Combine like terms.
Do y'all agree? And we'll combine like terms. On the bottom, do we want to do anything there? Do we want to multiply that h through or just leave it out? Yeah, you leave it out. That's the problem. Denominator is going to 0. If the numerator is going to 0 and the denominator is not going to 0, then that's fine. The result is 0. So it's really that, it's not that the numerator is 0, it's that the denominator is 0. That's causing us to not be able to evaluate this limit. So like we always did, just leave that out because that thing right there needs to go away at some point if we have hope of evaluating the limit. Okay, and like was said, we're combining like terms in the numerator. And so we just have 5h up top, this stuff on the bottom. And then we see those h's divide out, that h and that h. Alright, so we're left with something we can compute. The limit as h approaches 0. We have 5 on top and all this on bottom. So we should be able to evaluate this now. The issue was here that we've divided out. So that issue is now gone. What is this limit? It's going to be in terms of x, right? We weren't given, we just know x is some positive number. We get 5 up top, we get the square root of 5x plus 5 times 0. So we have the square root of 5x plus the other square root of 5x. So you just have 2 of those. Just make sure you add them. Sometimes if there's a question like this, sometimes people will multiply them and say it's 5 over 5x. You're adding those together, so make sure. So at this point right here, if you're going to go from here to here, I know it's a technical and nitpicky thing, but you need this limit. If you just say that, if you say this function right here is equal to this function, then that's not correct. That function's equal to that function only because we're computing the limit as h goes to 0. So at some point, make sure you have a limit there. Otherwise, you're saying 2 things are equal, which aren't really equal. Okay. So see y'all, Thursday? Let me know if y'all have any questions on the homework or whatever.